right, good afternoon, ladies and gentlemen. My name is Andreas Hildebrand. I'm working with ALC Networks. And ALC Networks is defining and developing the Ravenna audio or media over IP technology. And I'm going to tell you a bit about ST2110 from the audio side of things. So what are the differences and commonalities of audio of AES67 and the ST2110, mainly -30 definition. So what's in the bag for the AES67 supporters and what do they have to probably change? First of all, a very, very quick introduction overview of SMPTE for those you haven't heard. What all this is about, basically the idea is we have a full loaded video signal, an SDI signal, which contains video, audio and ancillary data, and ST2110 now defines to send them as elementary essence streams. So audio, video, and ancillary data will get transported across the network as individual streams, and well, synchronization of course is a big part of that that's coming up. On the network there may be a receiver which finally composes the signals back into an SDI signal again. So therefore we wouldn't have any reason to send elementary streams, but the benefit of ST2110 comes into game once we look at, for example, audio-only devices. Because with an SDA encapsulated signal, all the audio devices would have to receive the video as well, and which is a high bandwidth stream. But with ST2110, now the audio devices can just take the audio content out of the network, get the audio stream, process the audio stream, and also on the sender side, if we have a camera right here, it's sending a video stream and on ancillary data, and we have a microphone which is sending off the audio data. And ST2110 makes sure that all of this can happen synchronized, and that is something you just learned from Paul, how this basically works, but I will give you a quick overview of that in a minute as well. So SMPTE covering all these different aspects and technologies consists of a number of documents which are currently under draft and review by the standard committees. We have the -10 document, which basically defines the transport layer and synchronization mechanisms, so what protocols to be used and how the synchronization actually is achieved. -20 deals with the payload format of the uncompressed video. That's not part of my presentation. Neither is the -21 document, which actually defines the timing model for video senders. You can imagine that with video we have high bandwidth data and we need to have some very stringent timing on the network. -30 is the most important document for the audio part of SMPTE2110. That defines the payload format for linear audio, which is basically relaying back to AES67, which I will explain in a minute. -31 is a document which will be worked on, which takes care about AES3 transparent transport, which where we have a suggestion on the table, which is basically based on the AM824 format used by the Ravenna technology. -40 is the ancillary data for the SDI video, and -50 is the guidelines, the definitions, how AES67 or -30 and -40 work together with the existing 2022-6 fully encapsulated SDI streams. So that's the whole ST2110 suite of documents, and now we want to concentrate on the audio side of things. AES67 is the basis for audio transport in ST2110. What is AES67? It's a standard defined by the Audio Engineering Society, and it covers high performance streaming audio over IP interoperability. Published in 2013, what does AES67 actually cover? AES67, as written here, is interoperability guidelines for low latency professional audio using existing technologies and protocols wherever possible. That clearly excludes any non-IP networking, so any audio transport which is not based on IP. Low bandwidth media data compression is not part of it because that is not low latency. Low performance, wide area networking, public internet is not where AES67 can live on. And of course video, because it's an audio engineering standard, yes? So again, The focus is interoperability guidelines using existing protocols wherever possible. We did not want to invent yet another audio solution for transporting audio. We were actually looking at the existing applications or the existing technologies already transporting audio over IP. So basically the goal was, with AES67, we wanted to provide a standard which could be adopted by all the technology providers to actually make interoperability between these different technologies possible. Well, here's a quick view which does show this a bit more in an easy to grasp way. We have different technologies, you know, Dante, WheatNet, Ravenna, Livewire, QLearn, and there are others out there. They are all based on IP. But none of them actually can talk to each other, which is a pity. Well, not quite true, because Livewire and Ravenna were already able to exchange data with each other, but here's where AES67 comes into game, by defining interoperability guidelines and not replacing all these technologies, just defining what needs to be fulfilled in order to make these solutions interoperable. That was the goal of AES67. And from an application point of view, here's a quick example on how this could really help broadcasters. Let's say we have an event venue which runs a Dante system. Another one close by runs a QSys network inside. We have the OB van from the local broadcaster coming by. Not that one. We take this one. This is much better. That may run yet another technology inside the broadcasting van. And of course, as highlighted before, they can't exchange their signals except for having them to convert it to MADI or AS3 or whatever. So and now here's where AES67 comes into game. By complying to the AES67 interoperability guidelines, these different technology gear is now able to exchange their signals without having the need to convert to MADI. That's where AES67 actually helps from an application point of view. Needless to say that this goes on into the broadcasting station. There's also a scheme you're probably aware of, an IP-based scheme which is called ASIP, which is what we do with the codecs which are out there, transporting audio over IP by codecs, by audio codecs. And in a special mode, which is linear 16-bit, we also can send off AES67 audio into these codecs. So somehow, or on a limit base, ASIP codecs, ASIP compliant codecs can already take AES67 formatted audio directly in. That's AES67 from an application point of view. And now let's jump in and see what technologies need to be defined to actually achieve a set of interoperability guidelines and to make it happen. First of all, we need synchronization. And that is what Paul just presented about. Basically, synchronization is based on the distribution of absolute time by using PTP protocol. How does that work? Here's a very quick and brief recap of what Paul just said. Basically, all individual nodes, all devices participating on the network run their own internal clocks. However, these local clocks need to be precisely synchronized to the common network or wall clock. And this is achieved by PTP. And then, if I have precisely synchronized clocks, I can locally generate any desired media clock out of absolute time. So for audio, I can let the devices generate 48 kilohertz media clocks, or video devices can generate 90 kilohertz media clocks, and they all in sync because of the high precision of the precision time protocol. Here's a quick view how this works. We have a master clock instance on the system that can be a dedicated clock, like you will have here in the showcase. That can be, on smaller setups, individual nodes being capable of acting as master clock. In professional environment, that would be back reference to GPS, the most precise reference time available on Earth and beyond. We will have these individual devices, the slave clocks on the network in the devices, and through PTP, all these clocks are synchronized to the wall clock, to the common network clock. And once I have synchronized time, I let all these devices generate their local media clocks, or their media clocks locally, and since they refer to absolute time, they all have the same frequency and phase alignment. That's how we have synchronization and the media clocks there. The benefit of distributing time instead of frequency over the network is that I can generate any desired media clock in the devices. So I'm not limited to 48 kilohertz, and I even can do that concurrently on the network. So I can have video flows is 48, audio flows is 44.1, 96, no problem. Phase accuracy for audio, specifically for audio, this is required. In certain applications, we can receive phase accuracy according to AES11 out of PTP-based synchronization mechanism. We may have to employ PTP-capable switches in the network because they increase the time precision, finally resulting or coming down to the slave devices. And with the employment of GPS, we can have even time synchronization among facilities. In Frankfurt and Washington, we can have the same absolute time, the same absolute media clock in phase with each other by referencing to a traceable time. In a system, we need to understand, and that's now important to understand what the difference is between AES67, ST2110. We have basically 3 clocks in the system. The wall clock provided by the grandmaster and local copies of the wall clock in each individual device. We have a media clock, which is derived from the local copy of the wall clock. And there is an RTP clock, which is a stream clock of any individual stream, derived from the media clock. So this is how it looks like. Let's go to the picture. We have a sender, receiver, and the wall clock. We have local clocks. The local clocks are basically synchronized, disciplined by PTP. So we have the exact same time in the local devices. We have media clocks generating their output from the local clock. There might be an offset between the local clock and the media clock, but that is known at the startup of the node. The receiver has the same infrastructure, of course. As I said, the relation between the local clock and the media clock are known relationships at the startup of the node. And as you have heard, this is all referenced back to the 1st January of 1970, basically. Now there's a stream running between the nodes. That stream is absolutely frequency aligned or synchronized because of the media clocks derived from precise time, and they can also have accurate phasing. Well, what's even more important is the stream clock relies on the media clock, of course. I have a 48 kilohertz clock generating my media, and then the stream is conveyed with the stream clock, but it can have an offset. So the stream is not necessarily related back to the 1st January of 1970. But again, this offset is also known in the system. The sender does know the offset. And the offset actually is something which can be random, but it stays constant throughout the lifetime of that particular stream. It doesn't change. So, and then the offset information is actually conveyed to the receiver because the receiver needs to know what is the offset. When have the samples been generated? And that is conveyed through SDP so that the receiver actually knows for each individual sample in the stream when has this sample been created with reference to the local clock or the wall clock. So each individual sample has an exact reference to the wall clock. There might be offsets in between all these clocks, but these offsets are known because the sender knows its offset, the receiver knows its offset, and any stream can have an individual offset, and this is finally transported, signaled as an information through SDP. Of course, streams can receive a fixed determinable latency from sender to receiver by setting a deterministic play-out latency at the receiver. I know my sample is generated, let's say, at 1000, and if I set a latency of 1 second, just to make it as an example, I know it's always 1 second later when I play out that stream. In production, we are talking about milliseconds, of course. And most important, and that's the benefit of having an exact relation for each individual sample or frame or line in video, backwards to the local to the wall clock is independent streams, even being generated by independent devices, can now be correlated exactly with each other at any point in the network. If I have a microphone generating an audio signal and a camera generating a video signal, synchronized to PTP, then the streams are transported. The receiver, maybe a single receiver, receives the video and the audio stream. It exactly knows when has this video frame been generated, when has this audio frame been generated, regardless how long it actually took to transport over the network, even if they took different routes. And now, by time alignment, these streams can be exactly correlated to each other. This is the most basic essence of the whole ST2110 or AES67 mechanism. So, of course, AES67 needs to define about what protocols are in the game to transport the audio payload. RTP is being used, of course. Encoding and packet setup need to be defined in order to be interoperable. So we define 24 bits, also 16 bits, 48 kilohertz, 1 to 8 channels per stream, and 48 samples per packet as the mandatory requirements to be supported by any AES67 compliant receiver. Quality of service needs to be in the game, because you can easily imagine if you have a corporate network where you have this important audio, video traffic and other not so important web browsing, email, whatever, you have to prioritize your media traffic above all the other traffic. So differentiated services is being used. It's yet another standard which is available, which we just rely on. Connection management, we need to convey the SDP data, which also contains the offset, which is really important, but also other describing data, which describes the stream. Discovery is not part of AES67, neither it's part of SMPTE but we have other industry organizations taking up on this task, like the AMWA NMOS IS04, which actually covers discovery and registration, as well as portions of the connection management here. This is just to give you a full overview on what AES67 actually covers. And now let's jump into how does AES67 actually relate or differ from ST2110. So if we look at that into detail, there's the section of synchronization and timing. Basically, ST2110 calls for support of SMPTE 2059-2, which is a PTP operational profile. Now, AES67 mandates for the PTP default profile to be supported, but also suggests an AES67 media profile with higher performance parameters. Now, because the AES67 media profile, PTP media profile, and the SMPTE 2059 differ from each other, but have a range of overlap, AES and SMPTE jointly generated a report how to set up systems in an ST2110 environment to cover AES67 or to include the AES67 requirements as well. So baseline is, although SMPTE 2059 and AES67 PTP media profile are slightly different, there's a common overlap, there's a common ground, and this is described in the media profile. So the task is to set up the PTP operating profile in a way that it's understood by those devices purely being 2110 and those devices purely being AES67. So that's an engineering task, but it's already there. Currently under discussion is a parameter where you can decide if a device is prohibited from becoming a grandmaster on the system. This is something which is still a bit under consideration. The idea is that you try to prevent false grandmasters on the network, which will make the design of networks, the implementation of these systems a bit easier. I don't want to go into this in deep detail. Baseline is, if you implement PTP as a device manufacturer, just along the standard lines, there is no problem. And one further minor difference is just that AES67 defines that you have to reference back to a certain grandmaster clock. SMPTE 2110 goes further and says, okay, if the clock is traceable, we don't have to have the discrete GMID. If it's traceable, it means it's GPS reference. So this is just a slight lingo in the SDP file, actually. It's not any difference in the way AES67 or SMPTE work. It's a lingo type. So AES67 devices may have to adopt to accept this parameter, and then they actually do know what to do here. Now, this is the most important difference, actually. We talked about the different offsets, and SMPTE calls for a 0 offset of the RTP clock, of the RTP timestamps, with respect to the PTP network time. So in other words, every ST2110 streams is time-wise related back to the 1st January of 1970, the epoch of the PTP system. That is the difference, the only real difference, the only real thing which AES67 devices, if they want to participate within ST2110, need to be aware of. Because RTP actually, in the standard says, make this a random offset due to crypto attack problems. If you know the offset, crypto attack is easier than if you don't know the object. But SMPTE says, okay, for stream recovery, it would be easier for our devices if we know the offset up front before having to pull the SDP file, the information about the offset, again from the sender before we actually can run the stream. That's the motivation, that's the only difference. Technically, this is not a challenge at all. It just means that an AES67 sender needs to be able to work with a 0 offset instead of what the RTP standard calls a random offset. Now then, protocols. This was all timing and synchronization. In terms of protocols, RTCP, it's an accompanying protocol for RTP, is not required by SMPTE but if it's there, it must be tolerated. Nothing different from AES67 actually. AES67 also calls for support of SIP protocol for connection management with unicast streams. Not required by SMPTE as it covers multicast. Redundancy is suggested by 2110 based on another standard, 2022-7. So you can have or cannot have redundancy. If you implement redundancy, the only variation that is depart from 22-7 is you can't have identical IP source and destination addresses. This is a constraint which does not relate to AES67. Actually, it's a constraint 2110 puts on 2022-7. But it may apply to AES67 devices implementing redundancy, of course. So, and then SMPTE said, okay, if we have audio signals, audio channels in the stream, we want to know what these audio channels are. Is it just dual mono? Is it a stereo? Is it a 5.1? Or what's the setup? So they came up with a suggestion with an optional channel assignment map, which is conveyed through, again, this SDP. It's vital information, metadata information about what's in the stream, about the data of the stream. So this is an optional thing AES67 devices may or may not support. It's not a requirement here. Then we have 4 conformance level with respect to AES67 stream formatting. Very easy. We have level A, which actually says receivers need to be able to handle audio streams of 48 kilohertz, 1 to 8 audio channels in it, and a packet time of 1 millisecond. That is pure AES67 standard requirements. So any AES67 compatible receiver has automatic compliance with level A. But then the guys came up and said, okay, we want to have shorter latencies, because 1 millisecond packet time means at least 1 millisecond latency or larger on the network. We need a profile for smaller, for shorter latencies. 125 microsecond packetization time. Again, 1 to 8 channels, so level B receivers need to be able, of course, to cope with level A and these more stringent level B requirements. Again, this 125 microsecond is already a recommendation in AES67. It's nothing new. It's already there, but it's not mandatory. Then guys came out and said, okay, we need to want to convey MADI bundles with SMPTE 10-30. So level C says, okay, then a level C receiver needs to be able to cope with up to 64 channels per stream. That does not mean that a level A device cannot receive 64 channels. It just has to receive 8 streams with 8 channels each. And as they are fully synchronized, there is no difference, except for the packetization time, latency, in a level C stream. It makes no difference if you send off one stream with 64 channels in it, or 8 streams with just 8 channels in it. Due to the synchronization, we always have perfect synchronicity. And then finally, people were also worried about 96 kilohertz, and they said, okay, we need a level D conformance level. So if you want to support 96 kilohertz, use these setups, and we call it level D. So at the end, a manufacturer says, okay, my device is capable of SMPTE 2110-30 level B, or level C, or level D, or just level 8 because it's pure AES67. So baseline is, at the end, most AES67 devices are already, by design, by implementation, fully SMPTE 2110 compliant. The only real challenge is for those devices who could not yet set their streams with the 0 offset, send their streams with the 0 offset, because that is a hard requirement of 2110. But as I said, most of the AES67 devices already can generate these kind of streams. So that's about it. I covered a bit about the general idea of SMPTE 2110, about the synchronization, because that is the all-important stuff of 2110. How are signals synchronized among each other? And of course, how do AES67 devices comply to SMPTE 2110? And baseline here is most AES67 devices are already fully compliant with SMPTE 2110. And that's what we have over here. We have, I guess, 2 or 3 racks with AES67 audio-only devices. They all play nicely in the game because they understand the PTP. They run the recommendation PTP profile, which I mentioned before, and they can exchange audio with all the other devices, even coming from the video manufacturers. That's it from my side. If you want to have more specific input or information about audio, please feel free to come over and visit the Ravenna booth, which is just behind the Lava booth over there. Please feel free to visit the exhibition over here. A lot of interesting stuff going on. And please, please, if you have not scanned your badge yet and want to receive the presentations, not just mine, go behind the wall, see Tina, and ask to have your badge scanned. Thanks a lot, folks, and enjoy the rest of the show.